yeah, thank you for the introduction and the invitation. Today I'm reporting on joint work with Nissim, who's a PhD student at MIT, and his advisor, Scott Sheffield. So I want to begin my talk by discussing the main idea, basically, in this work, or the main general idea. It's actually very simple. I mean, it's basically just linear algebra, or if you want, functional analysis, because it's maybe infinite dimensional linear algebra. And it's just the simple fact that if you have an operator, G, say, which satisfies some sort of contraction estimate, such as the following. So suppose it's just a 1/2 contraction on some appropriate Banach space. Then any solution to linear inhomogeneous equations defined out of G, such as the following. So here F is some forcing term, and some element in your Banach space. And basically, once you have this contraction estimate, yeah, you can solve this inhomogeneous equation. And moreover, the solution is going to satisfy the following estimate on its norm. Right, so why is that? Well, you just use triangle inequality, and you use the contraction estimate, and then you bring the 1/2 over, multiply the 2 by both sides, and you get this bound, right? And so I kind of think about this like a PDE, and it's a linear and homogeneous PDE, maybe. And the point here is that you're getting a priori bounds to solutions to your equation just from this contraction estimate. Yeah, and so that's kind of the main general idea. Of course, kind of all the technical parts come into, finding the right function space and defining the right norm. I mean, that's where all the insights go into. But this is kind of the general point, how we're going to study lattice Young-Mills in this talk. Okay, so with that being said, maybe now let me also give some motivation for area law and why you care about it. And basically, this goes back to Wilson's paper from 1974. And so this paper actually defined lattice Young-Mills basically for the first time. I mean, maybe it was defined slightly earlier with some different motivations. But here the context was, by 1974, it was clear that gauge theory, Young-Mills theory, actually describes a standard model. And basically, a year ago, they finally realized this phenomenon of asymptotic freedom, and after that it was clear it actually describes like the strong interactions, quarks. And so Wilson wanted to study gauge theory, but maybe he didn't have all the background in the continuum language, because in the continuum it's all about connections on vector bundles. But what he's an expert in is statistical mechanics, right? So that's what he won a Nobel Prize for, phase transitions and statistical mechanics using renormalization group. And so he thought to put gauge theory on a lattice, and so that's where lattice Young-Mills comes from. And moreover, in this paper, he wanted to explain this phenomenon of quark confinement, which is basically this experimental observation that you never see isolated quarks in nature, at least at the current energy scales. And so he wanted some mathematical explanation of this, more or less. And what he arrived at was this area law, or what is known as Wilson's area law. Okay, I'll define all this notation later, but you have certain observables. I guess Wilson loops that we probably saw already, and you want to say that beta is this, as usual, the inverse temperature in your system, and you want to say that these observables have very rapid decay. So this L you should just take as a rectangular loop. And you think of this loop, both side lengths are going off to infinity, and you want to say the expectation, the Wilson loop expectation decays very, very rapidly, like e to the minus area. So here, of course, the constants could depend on your beta, but I'm not denoting that. And so somehow, there's some general argument giving you always perimeter decay, so e to the minus perimeter. But the point here is that usually the area is much larger than the perimeter for generic rectangular loop with both side lengths very large. And so this is much, much faster than kind of the generic argument. And in some sense, it's saying your system's very disordered. And basically, he had some sort of heuristic explanation for why, if you have this area law, then it to separate two quarks to large distance, it takes too much energy, and that's why you never see isolated quarks in nature. Right. And so later on, this criterion, so this is kind of a criterion for area law. Later on, it was kind of clarified that, okay, so first of all, you want to prove this in 4 dimensions. You want to prove this actually for all beta non-negative. So in this paper, you might have given some sort of proof when beta is small enough, but actually you want to prove it for all beta greater than or equal to 0. So the point is that even though beta can be arbitrarily large, but you still have this area law. And also, yeah, you want to prove it for, you recall lattice-Young-Mills has this parameter, which is this gauge group, and you want to prove it for SU3. So that's actually the theory describing quarks. Or, mathematically, it's also conjecture to prove it for G, any non-abelian V group. And that's kind of, well, anyways. Yeah. So, okay, this is the thing that you actually want to prove in physics, but mathematically it'd already be quite interesting to prove this conjecture for any non-abelian V group. So that's a conjecture, basically. Was I going to say something here? Let's see my notes. Okay, I guess not. Okay, so with that motivation being said, I'll define the model now. So I'll set some notation. So what is lattice-Young-Mills? So okay, here's a bunch of notation. We're going to fix n to be some parameter greater than or equal to 1. For my talk, this always parameterizes the size of my gauge group. So we're going to take the group G to be UN. Eventually, you actually want SU3, but somehow it's the simplest to consider the unitary group rather than the special unitary group. In principle, our results will also apply to SUN and SON as well, but maybe there's just some extra steps that we didn't really talk about. So we just did it for UN. All right, so that's some notation. Okay, dimension at least 2. Okay, this parameter beta greater than or equal to 0. And then, yeah, as usual, you have your lattice lambda, which is subset of ZD. Oh, yeah, also the thing that I forgot to mention earlier was that this area law thing, it's really a statement about long distance behavior of your gauge theory. And so that's why you're kind of maybe willing to have this ultraviolet cutoff, so you just go to a lattice. So even if you haven't constructed the continuum theory, it's kind of a different setting. I mean, it's long distance behavior, not short distance. So, okay, you just have some cutoff, you go to the lattice, and you ask about long distance behavior on your lattice. Anyways, right. So that's the lattice. And yeah, so lattice gauge theory is a probability measure on a space of functions of edges of your lattice into your group G. So here E plus, so I'm also setting notation here, that's a set of positively oriented edges. But as usual, and I guess we've seen this in previous talks, you kind of just extend this to negatively oriented edges in the natural way. Okay, so you just assign a negative edge, the inverse of the matrix you assign to the positive edge. Somehow this is natural from the way these things arise from the continuum. You discretize the connection on a vector bundle, and this is just how homonymies of connections transform. But anyways, right. And now I can maybe just set my notation for the measure. So mu lambda beta, that is Young-Mills. So the probability measure on these U's. And so the way I write it, okay, so as usual, you have the partition function, and you have a product over plaquettes of my lattice. So this is, again, setting some notation. So a set of oriented plaquettes of the lattice, of exponential, beta, real part, trace of UP, and then all with respect to product R measure. And that's what I write by DU. So, so this last point of notation, I'm not going to write it out, but this plaquette variable UP, so this is slightly abusing notation, but it's just, if you have a oriented plaquette, you traverse the edges of on the boundary of your plaquette, and you take the product of your group elements. So that's what this plaquette variable is. And so that's this lattice-Young-Mills theory. And yeah, so just briefly, how do you think about this measure? Well, yeah, so this parameter beta, you would think governs the amount of order or disorder in your system, right? So when beta is small, your system's very disordered. And when beta is large, you kind of, typical configurations want to have real trace of P be maximal. And what does it mean to be maximal? It actually means that this plaquette variable wants to be close to the identity, because it's maximized that n, the n by n group. And so basically, when beta is large, you would think that typically most plaquette variables are close to the identity. And so it's kind of analogous, everything just one dimension higher versus the usual spin systems, right? So usually in spin systems, you put spins on the vertices, you have them align across edges. Here you put spins on the edges and you have them align across plaquettes. So that's how you kind of think about it. Right. So that's the model. And now I think I want to define what Wilson loops are. Right. Okay, so let me just set some more notation. Given a loop L, which I represent by its sequence of directed edges, let's let the associated loop variable UL be the product of the edges on my loop. So again, you should think of this as I'm traversing this loop. Every edge you take, you multiply by the assigned group element. And yeah, and the corresponding continuum thing would be the holonomy of your loop, or your connection along this loop. And then let's define this loop observable WL. It's a function on lattice gauge configurations, and it's simply just the normalized trace of your loop variable. And normalized trace is just 1 over n times the usual trace. Right. So that's basically this observable appearing here. And as usual, this angle brackets notation just means expectation with respect to your measure. Okay, so so I think there's one more piece of notation before I can talk about other stuff. So let's see. And so now, for reasons that I will need later, given now a string S, and by a string I just mean a collection of loops. So L1 through Ln. Let's let the associated string observable just be the product of the loop observable. Okay, so that's a definition. Yeah, and then one remark that I will come back to later is that if your loop is empty, right, your loop could just have no edges, then by definition, your loop variable should just be the identity matrix. Yeah.
I have a kind of a question out of curiosity. Do you know any reason why people don't just look at the real part of the trace for the Wilson loop? And is it important because they're both the real and imaginary part?
I think there might be some distributional symmetry which tells you it's actually just real valued. But maybe not. Yeah, but I don't know if it's actually complex, but I don't know why people just out of curiosity. Yeah. Okay, if your loop is just empty, then kind of by definition, you take your loop variable to be the identity, which means the loop observable is just 1. It's normalized trace of your identity matrix. So that's a remark. Okay, so that's the model. And so before I state the main results, maybe let me just briefly, very briefly survey some previous results in 4 dimensions. And so, there's many references I could give, and we give them in the paper. In the talk, let me just talk about the most relevant references to our talk. So I'm going to draw a graph. So the x-axis is your value n, which governs the signs of your matrix group. And the y-axis is your inverse temperature parameter beta. And so really the graph just starts at n equals 1, right? Because, okay, there's not really a unitary group of 1/2 or 0. So we really start at n equals 1. And so, okay, maybe the most classical result is in this area is by Osterwalder-Seiler, who showed that for every n, there exists a beta below which you have area law. So that's maybe from 1978. Yeah, and so I try to draw this curve like 1 over n. So this is like proportional to 1 over n. And if you inspect their proof, that's basically what their threshold gives. So for every n, there exists a beta that's basically 1 over n, below which you have area law. So let me shade this region. Yeah, and then another classical result is that if you just focus on n equals 1, which is the abelian case, then actually you have deconfinement. So actually above some large enough beta, you no longer actually have the area law. You actually decay like perimeter. There's a lower bound, which is again much slower than area. Right? So this dashed line means you no longer have area law below. And this is all just along the line n equals 1, so this vertical line. Right, so this was proven by Froelich and Spencer. In 1982, and that's basically, I mean, this point is known as, just like in the XY model, it's known as the VKT transition. And basically their proof is very analogous between 2D XY and 4D U1 gauge theory. I mean, you just replace 0 forms by 1 forms, almost, basically. Right, so that's another result. And then, yeah, so the main result, our main result is basically, instead of this 1 over n line, you basically have a straight line, or a constant. I'll say it formally soon. Which basically means instead of for every n, there exists a beta, below which you have area law. We're saying that there actually exists a beta small enough such below which you have area law for all n. The reversal of quantifiers. So that's how you visualize the main result, but I'll state it. Yeah. Oh, any questions?
Do you know that do you actually know that you improve the beta for n equals 3?
What do you mean by proof the? Oh, I see. Oh no.
They had some critical beta, and you get better than get a bigger range for n equals 3.
Yeah, no. So you should really think of our result as a large n result. Like we really just take n to be super large in our paper. So we're really improving this region when n is large enough. And kind of that's one thing that I want to talk about in the proof. It should really be easier to prove area law when n is large. I mean, usually in these large n models, things become simpler, not more difficult. Which is why this parameter is, I mean, this regime is somewhat unnatural. The fact that the proof kind of gives something decaying with it. So that's kind of our point. But yeah, so this point here at which our improvement kicks in, you know, if you track the constants in our paper, it might actually be 10 to the 10. Okay, so I didn't draw it to scale. Yeah, I mean, obviously we didn't optimize the constants, but you really think of it as large n. Like you're going to take n to be super large. And also this, and then, yeah, and then we also take beta to be super small.
We don't do that hooked scaling.
Yeah, so I'll comment on that. Right, so, yeah, so there's this natural regime that should be the limit of our methods, which is this Tahoe scaling, which I'll mention, which is basically something that's linear in n. And so that's a line that's linear in n. I'll comment a bit later why this is kind of the natural, would be the natural limit of our methods, like this type of contraction argument. And, right, so you would want to prove, and it's something maybe we're currently thinking about, although maybe we don't have exactly super concrete we have some ideas, but nothing's really, not that we know how to do it. But I should also mention that, so in this regime, the Osterwalder-Seiler, in addition to area law, they proved mass gap in this regime. So basically you have exponential decay of correlations. In principle, okay, we didn't do in the paper, but if you work a bit more, you would get exponential decay in this regime as well, in our paper. But actually mass gap in this linear regime was proven earlier by Hao, Rongchan, and Xianchan. And okay, the year is maybe 23, something like this. So for this mass gap. And it's this nice observation that actually in this regime you can do Bakary-Emery, basically. So you actually have log Sobolev below this line. And once you have log Sobolev, then you would expect to get exponential decay of correlations. Right, so it's kind of, okay. That's also kind of why this is maybe a natural limit of our methods, because, yeah.
Here is UN, so our result is SU.
Yeah, right. So, okay, mass gap for SUN, SON. I mean, the only reason I guess you didn't do UN is because the Ricci curvature, there's some zero directions. But I guess in principle you could, I mean, I guess no one ever wrote it down, but it should be possible to do your result for UN as well.
For UN, there's also this further correlation inequality that compares with the center or whatever. What does that give?
Yeah,
Is that
so
you just need to do the ZN, I guess.
yeah, exactly. So I think, I mean, we checked this, and it's a remark in our paper. Like you give up in your beta, and basically what you give up is basically this 1/n. You have to go to like higher beta.
So for ZN,
I mean, ZN eventually you
the true-
deconfine.
what is, I mean, for ZN, what is expected to be, I mean, here the truth is expected to be everything as soon as n is bigger than 2, right?
Yeah, basically. Yeah.
But for ZN, I guess, in your picture, what is the line? I mean, then it's not everything, but
I think basically once n becomes large enough, you expect to basically approximate the U1 theory. It's like filling out the circle. And so probably the transition point should be kind of converging to the 1 for U1. And then like you give up this 1/n from product, which is why you. I mean, yeah, so that's for SUN though, because the center of SUN is CN. For our like unitary group, you would start with the U1 results, which is just here, basically. But then you still give up 1/n from what's further. Yeah, but as I said, okay, this is somehow the natural regime that you would want to prove. Of course, let me do the draw out the conjecture, which is, as Roland said, basically everything beyond. Okay, so this is 10 to the 10.
now it's 2.
Now so everything here should be area left. Okay. Right, so, okay, I'll just formally state our main results, but basically it's pictured here, so. I should also say that you might be aware of this paper by Chatterjee, which says that if you have mass gap, then you just get confinement. And this paper here by Hao, Rongchan, and Xianchan prove mass gap. But if you look closely, the mass gap assumption that Chatterjee assumes seems somewhat stronger. At least it appears to us. I mean, it's not obvious to us. You just get that immediately from log Sobolev. So yeah, that's why, at least to us, it doesn't appear that the mass gap that they prove immediately proves area law. But maybe something like that could be made to work. Okay, so
Maybe an interesting remark for the Heisenberg model, there's an analogous picture in 2D. And there the n there's an n log n that's been proved, which was Antti Kupiainen's PhD thesis.
I see,
So you
interesting.
got above that line, but he worked hard.
This was by like renormalization group or?
No, it was reflection positivity and some other. I never read the paper carefully, but I think he was using reflection positivity and so. But anyway, I think he got n log n.
I see.
I mean, I think his thesis problem was to prove it for all.
Right. Okay, so the theorem, so technically our result applies to any dimension, but it really only gives improvement in 4 dimension. In 3 dimension, you kind of know area log for all n. Yeah, for all n, due to some other results, but yeah, okay, I'll just state the theorem in any dimension. So there exists some small enough constant, theta 0. Principle depends on the dimension, such that, let's see, there exists constants, well, such that for all n, there exists constants c and middle Cn, such that, well, the above estimate holds for all rectangular loops. So. That's the results. So comments on these constants. So this C, you can just take an independent of n. Now, it's somewhat artifact of our proof that this C here actually decays with n. I mean, that's definitely not going to be the right thing, but that's just what our proof gives. And actually our proof, but this is the result of some interpolation things. I mean, if you take a rectangular loop where both side lengths are large enough, depending on n, then you would get a constant here that doesn't really does not depend on n. So, but I wanted to state a nice result where this C is just, like say 10. And then if I want something like that, then I need this to be decaying in. But anyway, small comment. Yeah, so that's the result. But really, you just picture it like this. And like I said, it's really a statement about large enough f, because if n is below 10 to the 10, you can just use the Osterwalder-Seiler result. So we really start kicking in once n is large enough. And yeah, you should think of the beta 0 as like 10 to the minus 10, like I wrote here. Okay, so that's yeah, maybe some remarks. The first is that I guess I already mentioned this earlier, but should also work for E is equal to SUN and SON. Looks like there's maybe a couple extra terms you have to estimate, but I don't see inherent difficulty. Second remark is that, so technically there's a finite lattice here, but all your estimates are uniform in your lattice lambda, right? Because you really want your sequence of rectangular loops tending to infinity. In order to do that, you have to also let your lattice tend to infinity. I mean, of course, this implies that for any subsequential limit, the same estimate holds. And actually in this regime, you expect the infinite volume limit to just be unique. And that's proven up in this paper for SUN and SON by Hao, Rongshan, Xianshan. And yeah, I guess somehow by adapting the proof should also work for UN. And if you do that, then you know you have a unique infinite volume limit. And then you can just state this in infinite volume. Yeah, so that's side remark. Any questions? Okay. Let's see. Okay, yeah, so now in my remaining like 20 minutes, let me just talk about some elements of the proof. So yeah, let's start with this surface sum picture. And so this goes back to recent work by myself, Park, and Scott. I guess came out in arXiv in 23. And this result basically gave a formula for arbitrary Wilson string expectations. So you don't have to take a single loop, but you can take a collection of loops, like a string. And you get a formula in terms of a sum over surfaces, which you basically kind of imagine as follows. So this is very schematic. So maybe your string is just made out of two loops, L1 and L2. And to compute this expectation, you have to perform a sum over all surfaces spanning your two loops. So maybe it's like this. These surfaces could be arbitrary genus. So maybe I'll draw some handles. And then also you have this thing that you could just have close connected components. I mean, if you're familiar with these loop representations of spin ON, something similar occurs here. Like you could have just these closed components just in the void. Somehow you have to perform a sum over all surfaces, an example which is given in this paper, in this picture, and that'll compute for you the Wilson loop expectation. It's not just a sum, it's a weighted sum. So each surface comes with a weight. So let me describe what that is. And so the weight is so there's three terms to the weight. The first term is actually in terms of the area of your surface. And it's very nice. It looks like beta over n to the area of your surface. The area is roughly the number of plaquettes you use. Again, I drew this schematically, but you should think of all this as living in your lattice. And roughly speaking, these surfaces are made out of gluing together lattice plaquettes, but that's not exactly how it's defined. So yeah, I'm not going to go into detail about how exactly these surfaces are defined. But roughly speaking, they're made out of gluing together plaquettes, in which case the area is just the number of plaquettes you use. And so this term is very nice because, especially in our regime, where beta is 10 to the minus 10 and is 10 to the 10, you see you pay a huge cost to have surfaces of large area. And if you have a loop, you must have a surface spanning that loop. And so that's why you maybe expect to see area law in this regime. And moreover, not in this regime, but in this linear regime, when this constant is small enough. Because if beta is a tiny constant times n, you're still paying area in the area. But okay, we're just handling this horizontal line here. Okay, so that's the first weight. So that's a very nice weight. The second weight is n to the Euler characteristic. So again, n is the dimension, the size of your matrix group. And the Euler characteristic basically, you're basically penalizing having many handles, right? Especially if n is large, right? We think of n as 10 to the 10. So when n is super large, you kind of want most of your surfaces to be planar. Because otherwise you just pay too much in your Euler characteristic. I mean, that's also fine. I mean, for the model, right? That's a nice weight as well. It's easy to understand. And then the last weight is really kind of where a lot of we were kind of puzzling over for quite a while, which is the so-called Weingarten weight. Let me not define it. I will just say that it's complicated. And part of trying to figure out how you work with these surfaces is trying to figure out how you work with this complicated weight. I mean, it's defined out of, for instance, the representation theory of Sn. It's defined using characters of Sn. There's no point in giving the expression. It's just somewhat complicated. Right? So the question basically, we started thinking about this. I mean, how do you understand this Weingarten weight? The point is that at large n, it simplifies greatly. So first of all, if you took n to infinity, there's a very explicit formula for this in terms of Catalan numbers. And then you can ask, well, how do you understand this if n is large but finite? And then there's actually like expansions for this function in terms of powers of 1 over n squared. So that's kind of how we started thinking about this. But then eventually we kind of took a step back and thought about how you actually analyze surface sums in general. Suppose you just have a random planar map, like a model random planar map. How do people actually work with them? And typically you explore them. Right? You define some sort of exploration process where you reveal one face at a time. I mean, your random planar map has a boundary, and at each step you choose an edge on the boundary to reveal the face at. And this is what is called a filling process. And this is a very nice Markovian process, and then through analyzing this process, you can prove things about random planar maps. And also you can prove things about enumeration. I mean, this type of, the partition function analog of this type of thing would be, for example, Tut's recursion. And this is very classical. I mean, Tut used his recursion or equation to prove very precise enumeration results about the number of random planar maps, right? So kind of the point is that to analyze surface sums, you don't just look at this weighted sum. You just try to explore them one phase at a time, right? And so then the question is, yeah, so does there exist something like that in Yang-Mills?
Does the Weingarten weight have signs at n is large?
Yeah. So it always has signs even in the large n limit. Yeah.
I mean, the Weingarten function I'm aware of is a function of a permutation, but I don't see, is there a permutation here defined by the surface?
It's kind of hidden in that, like, for instance, to draw an analogy, when you do just usual Wick's formula for Gaussians, you have to like sum over all pairings, but the pairings just all get weight 1. It's like each pairing has the same weight. Here, when you compute unitary group integrals, there is some sort of sum over pairings hidden in this. And these pairings no longer get weight 1, they just get this Weingarten weight. And so it's kind of hidden in how you define these surfaces.
Yeah, but the Weingarten is for a certain permutation, the Weingarten of sigma. But
Yeah.
how do you, here you have a surface, how do you get the permutation from that surface?
Yeah, so these pairings tell you how you glue together plaquettes, roughly, and the pairings you interpret as permutations. Yeah, and so, yeah, you would mention the signs in these surface sums for Yang-Mills in this talk, and that comes from the Weingarten weight. Yeah. And it persists in the large end limit. Right. Okay, so now let me erase this board. So yeah, I asked the question just now that does there exist some analog of this Tut's recursion in Yang-Mills, at least for these surface sums that we see in Yang-Mills? So the answer is yes. And we already saw it already earlier in the workshop. And the answer is, the analog is the master loop equation. So to state this equation, let's set some notation. So phi will be this Wilson loop expectation. Or sorry, Wilson string expectation. So phi is a function on strings. Okay. And the master loop equation is an equation satisfied by these string expectations. And the reason why you want to work with strings is because if you just work with loops, you don't really get a closed equation. Like one loop could become 2 loops. So in general, you have to work with collections of loops. And what does it look like? So okay, I'll write out the formula and then say a couple words about each of the terms. Okay, so I just wrote out a bunch of terms on the right-hand side. How do you think about these? So basically, we're expressing the string expectation as a weighted sum of neighboring string expectations. The neighboring strings are split into 3 categories. So splittings, so there's this math BBS, mergers, that's a math BBM, and deformations, that's a D, okay? And then within each category, there's 2 types. So there's a positive and negative for each category. So in total, you actually have 6 types of neighboring strings. And And the notation here is that, okay, so this is a sum over actually two disjoint sets, positive splittings and negative splittings. When you sum over positive splittings, you get a minus. When you sum over negative splittings, you get a plus. So that's the notation here. It's just some compact notation, so I don't have to write out 3 more sums. And similarly here, so there's a minus plus and a plus minus, minus plus and a plus minus. Right? And so why can you think about this as basically an exploration, conditioning on the first step of an exploration process for those surfaces coming from Young mills? Well, basically, okay, what's the splitting? It's what happens when your boundary splits from 1 loop into 2 loops. Okay, so that could happen when you're exploring. So for instance, a splitting, let me try to draw a schematic surface. So maybe you're like you're exploring your surface, you're keeping track of your current boundary. At some point you kind of branch off, and that's the point where 1 loop splits into 2. Right? So it's a splitting of a string, but here you're like picking one of the loops in your string to explore at. So one of the loops in your string becomes 2. But, yeah. And so that's a splitting term. A merger term happens when 2 loops become 1. And that's going to happen if you create a handle, basically. So basically, if you're exploring your surface, and at some point you realize you actually made a handle, that's coming out of this merger term. And that is why you have this 1 over n squared in front. Because every time you create a handle, your other characteristic decreases by 2. So that's why you must have this 1 over n squared. And then this deformation comes when you're basically exploring plaquettes of your surface. Right? So because this beta over n corresponds to the weight beta over n to the area up there, every time you do a deformation, you basically saw 1 extra unit of area in your surface. Right? And so that's basically how you think about the master loop equation in terms of this surface exploration. Right? And kind of the whole point here is that it's linear, right? It's linear in phi as a function on strings. It kind of actually looks homogeneous, right? Because it kind of looks like I don't have a forcing term f on the right-hand side. But in fact, I do, because it could have happened that one of these neighboring strings was the empty string. And you recall we kind of have this convention that up there, that if I have an empty string, it's just 1, right? So this is kind of the base case of your recursion. If you ever see an empty string or empty loop, it's just 1 on the right-hand side. And so that's really what the forcing term, that's how it appears. And this would happen when you basically explored your entire surface. Once you're done exploring your surface, your boundary is empty, and you saw everything. Right, so that's the master loop equation. And so maybe let me define the right-hand side of this as m phi. So m is maybe the g plus f, or g phi plus f in my beginning discussion. Right, and so that's kind of the main, again, to reiterate the main idea, you want to study Wilson loop expectations via this master loop equation. Because it is a nice linear equation, and you can hope to prove some sort of a priori bound to solutions to this equation. Right, and so how do you prove some type of a priori bound in this case? Well, I mean, what is your goal, right? So you want to find a norm on basically a set of functions, say g, from the set of strings to say complex numbers. So it's a norm on this function space such that you have 2 properties. The first thing is that you want to prove area law, so your norm better imply that. So you want your norm to have the property that if I evaluate the function at the rectangular loop, then it's actually basically e to the minus the area of the loop times the norm. So I want my norm to imply area decay, because that's what I'm trying to prove in the end. And secondly, I want to prove this contraction estimate for this m. Right? So I want to show that this m, so this property 1 is just for all rectangular loops. in the end, we really only care about rectangular loops for area law. So we just want the norm to have this for rectangular loops. The second property is that, yeah, you have this contraction estimate for the n. So, plus 1. I mean, the 1 could be any constant, doesn't matter, right? So you want to design a norm satisfying these two properties, because if you can, then you immediately get that, well, area law holds. Right. Because you automatically, I mean, phi is a solution to this equation. This function, which is just the Wilson loop expectation. And so all you're trying to do is derive an a priori estimate for a solution to this equation. Right. So that's kind of the main general idea of the talk, as I said in the beginning. Any questions? Okay, so yeah, there's definitely no way I'm going to get into how we define this norm. Let me just give some general remarks.
Is the one kind of weird? So M is linear. It's not a linear operator, or is it a linear operator?
It's inhomogeneous.
It's not an operator. It's yeah.
Yeah, it's really like the right-hand side of it. Maps phi to g phi plus f. So the 1 is really like the norm of f. Okay.
If you have this recursion, do you think the solution has dichotomy, either decays fast or maybe stay bounded?
I mean, you always have perimeter decay. So maybe you want some sort of sharpness result, like if you decay faster than perimeter, then you have area. And you guys haven't really thought about using some sort of fixed point method to prove something like that. But maybe, yeah. And okay, so I should say that we're not really the first ones to think about this kind of PD approach to studying Wilson loop expectations. I think, to my knowledge, this was first introduced in a paper of Chatterjee, who studied a large n limit. So let me talk about that. Yeah, so there was this paper of Chatterjee, which I guess was published in 2019, but probably came out in archive in 2016, where he found a norm which basically satisfies those two properties for the large n limit. So the large n limit, you would actually take it along this line. So there's the 't Hooft scaling, because these Wilson loop expectations converge when n goes to infinity, and they satisfy the limiting equation, which is when you just take n to infinity up there. And you have to scale beta linearly in n, otherwise you just get kind of a trivial thing. If you scale beta linearly in n and take n to infinity, what happens is that basically the merger term drops out. And that's consistent with the fact that you just get planar maps in the large n limit. And also consistent with the fact that, yeah, when you weight by n to the Euler characteristic and then send n to infinity, well, you're just going to have planar maps in that limit. And so he found a norm when n goes to infinity. I'm not going to describe it. And you might think that since we're taking n large enough, even if you take n to be, so again, you basically erase the merger term and found a norm. And instead of beta over n, just take beta. So that's kind of the equation he was looking at. And you might think that if you just take n to be 10 to the 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 10, you can just perturb his norm and get something that just works. And unfortunately, that doesn't seem to be the case. At least we couldn't figure out how. Actually, I mean, as soon as n is finite, that merger term kind of, you can't really think of as perturbative. I mean, I think in the end it is, it has to be, but we don't know how to do it, basically. And that's kind of the main obstacle in this work. How do you get around having this merger term here? As soon as n is finite, it's a huge problem. And somehow that's, maybe it's inherent because it's well known that models of large genus maps are complicated. Right? As soon as n is finite, you could have maps of arbitrarily high genus. And it's very hard to enumerate maps of very high genus, for instance. And so somehow it might just be an inherent problem that very quantitatively understanding the contribution of large genus services, it's just different from understanding the limiting case. You need quantitative balance. So even if n is super large, you still need to do something extra. At least that's what it seems. And so yeah, in the end, okay, we managed to find some norm by going to some sort of truncated model where the merger term is not as bad. But I'm out of time, so I'll end here.